A magnetic field is a region around a magnet that experiences a force exerted by the magnet. In other words, it describes the distribution of magnetic force in the space around and within something magnetic in nature.
In order to understand what a magnetic field is, it is important to say that a magnetic field is a vector field. What is a vector field? First, we need to recall what a vector quantity is. A vector quantity is a quantity that has both magnitude and direction. When we measure the velocity of a car, we take into account its speed and direction it is traveling in. A vector field, then, is a region where every single point of the space within is assigned a specific value of a chosen vector quantity. The value is called a vector, represented simply as an arrow. The size of the arrow represents how high or low the magnitude or value of the vector quantity is at that point in space. The arrow itself obviously represents the direction of the quantity.
The easiest example of a vector field is a weather map that visualizes the speed and direction of winds in an area. In the map, the size of the arrows represents the speed of the wind current at a point in the world. The direction of the arrows represent where it's traveling to. Now, back to magnetic fields. In a magnetic vector field, the size of the vector represents the strength of the magnetic force at each point in space. The arrow tells the direction of the magnetic force experienced if a moving charged particle would be placed at that point.
Wow, they look exactly like electric fields. There's even a point of positive charge at the North Pole and a point of negative charge at the South Pole.
Not quite. Based from what we've seen in the picture, it looks like the North Pole serves as the source of magnetic field vectors while the South Pole absorbs them, like electric charges and electric fields. Unlike poles attract each other and like poles repel each other, much like electric charges in an electric field. However, the poles of a magnetic field are actually not the start nor the end of magnetic field vectors. As you can see in the visual, this is what a magnetic field actually looks like. The magnetic field vectors continue to flow through the magnet. They don't actually emanate from the North Pole or absorbed by the South Pole. The South Pole is where the magnetic field lines come back so it looks like it absorbs them, while the North Pole is where the magnetic field lines come out so it looks like it produces them. You can't pinpoint where the magnetic field vectors come from or where they will end up. The magnetic field is a continuous loop. This entire phenomenon is described in Gauss's law for magnetism, which, in very simple terms, states that at any region in the magnetic field, the amount of magnetic field vectors directed into a region in the field is always equal to the amount of magnetic field vectors directed out of a region in the field. In other words, there is no source or absorber of magnetic field lines or vectors. Therefore, there is no such thing as magnetic charge. Only electric charges exist.
Well, what is the source of magnetic force if electric fields can exist without electric charge? Then how do magnet field even exist?
Actually, electric fields and magnetic fields have the same source, electric charge. However, unlike electric fields, magnetic fields are only created when an electric charge or a group of electric charges, known as a current, are moving. You can visualize this by making a thumbs up with your right hand. Your thumb and the direction it is pointing at represents the flow of electric charges, while the rest of your fingers represents the magnetic field created by it, which is wrapping around the current.
Hold on, how does an electric charge moving generate a magnetic field if a moving electric charge is needed for a magnetic field? Then how do you explain how regular magnets work? They're obviously not electric currents.
Okay, let's slow down and take these questions one at a time. Let's start with, how does an electric charge moving generate a magnetic field? Imagine a pot of water simmering on a stove. The flame beneath the pot represents the flow of energy or heat, analogous to the flow of electric charge in a wire. Just as the flame's heat flows from the bottom to the surface of the water, causing it to circulate and form convection currents. Electric charges moving through a wire generate a magnetic field around the wire, similar to how the flow of heat pushes the water to form convection currents. The flow of electric charges exerts a force on the area surrounding it, forming magnetism.
Now that we've explained how a moving electric charge produces a magnetic field, it's time to answer the next question. If a moving electric charge is needed for a magnetic field, then how do you explain how regular magnets work? They're obviously not electric currents.
The thing is, electric charges are moving in magnets, despite there being no electricity. They just happen at the atomic and subatomic level.
Let's begin by introducing concepts and connecting them one by one. First, when two magnets with opposing orientations are put next to each other, both of their magnetic fields cancel each other out. Second, electrons are magnets and have a magnetic field. This is because electrons and all subatomic particles have a property called intrinsic angular momentum, also known as spin. Momentum is a type of motion, and as long as a charge, or electron, is in motion, it generates a magnetic field. Third, the quantum spin of an electron also determines the orientation of the electron and therefore the orientation of its magnetic field. Fourth, in atoms, the electrons that orbit it are found in its orbitals. We can find their electron configuration with something you might have already seen before, orbital diagrams. For atoms to be magnetic, the electron configuration of its outermost orbital shell must have most of its electrons be unpaired. This is because when electrons are paired as shown in an orbital diagram, one electron should have their quantum spin oriented up and the other must be oriented down. Once they are paired and have opposite orientations, the magnetic fields of both electrons cancel out. However, if the orbital shell is filled halfway or close to it, there is not enough electrons to form pairs, meaning there is no cancellation of magnetic fields, and they are allowed to form a stronger magnetic field, making the entire atom magnetic. Fifth, in order for a material to be magnetic, however, like the bar magnets, all of its atoms should be magnetic. Not only that, every single magnetic field of every magnetic atom of that material must be pointing in the same direction, meaning they must have the same orientation. The atoms might be magnetic, but if their individual magnetic fields are oriented at very different directions, they might cancel out or weaken each other, rendering the material not magnetic. And that is how permanent magnets work.